in diffusion flames we could actually look at two situations that are slightly different from each other. One is a Coflow diffusion flame, or the other one is a counterflow diffusion flame. We'll talk a little bit about each of these. The reason why we aim to talk about a Coflow diffusion flame is because we are now talking about two different reactants that are approaching each other. The question is, when you now say flow, you are now talking about how do they convect. Okay. Previously, earlier we were talking about how they mix with each other. Mixing is essentially depending upon primarily the concentration gradient that is prevailing for each species to mix into each other. But the question about the configuration of the flame is how do the reactants flow to each other. In the case of premixed flames, when we are saying premixed, that means the reactants were mixed with each other, so that means they flow together. There is no way you're going to have the reactants flow from different sides or something of that sort, right? But not the moment you're now talking about diffusion flames where the reactants are coming differently, and then they have to mix at the flame, then you could now begin to talk about these things, right? So a Coflow diffusion flame a typical configuration would be where you have, for example, in a duct you have a splitter plate and you have a fuel on one side and oxidizer on the other side, and the splitter plate terminates at the lip of at its lip, and then you now have a mixing region. That means as the flow is going up like this, the fuel mixes like this and the oxidizer mixes like that, right? And somewhere in there you're expecting a flame to happen because that's the flame is where they mix with each other, right? So this is what's called as a Coflow configuration. There are several situations which actually mimic this. For example, if you now think about like a Bunsen burner, right? So you have a fuel that's coming in, the oxidizer is actually ambient, it's not exactly flowing, but effectively you have a flow that is being set up by the fuel, and of course the products are also actually flowing outward because they are hot, and in a buoyancy driven flow they basically go upward, and therefore you have an entrainment of the air. So the entrainment of the air is also causing a locally Coflow situation as far as the flame is concerned. And you could also have like a burner within a duct where you have a fuel in the middle, an oxidizer in the outer annulus, and so on. So all these things are basically like a Coflow situation. A counterflow situation is where you are essentially trying to have fuel come in this way and oxidizer coming this way, and you now see, if you didn't want to have any shear layer effects in the Coflow case, you would now say equal velocities for both the fuel and oxidizer. That means this is coming in at a velocity u, this is coming in at a velocity u, same velocity. So you don't necessarily have like a shear layer between the two, and you are focusing mainly on the species mixing rather than any momentum mixing and all that stuff. Similarly, you could also think about in the counterflow situation a counterflow at the same velocity, for example. So if you now think about this, and typical examples would be like what's called as an opposed jet burner. So if you now have like a jet here and a jet here, this is like the nozzle for the jet, or the jet mouth, if you will, and then essentially they are now apart by about a distance h, let's say, right, and then they are coming in with a certain velocity. So what this is going to do is you're going to have a flow that's going to go like that, right, and as the fuel is flowing like this and the oxidizer is flowing like this, they are mixing with each other, and when they mix with each other, somewhere in there, not necessarily in the middle of the flow, but somewhere in there you're going to have a flame that is a diffusion flame. Right, and this is a flame where you can actually hope to establish something that is very flat. The flame would be quite flat because the mixing is going to happen equally on both sides, except now the problem is you don't have a uniform velocity field for the flame. In fact, you're now going to have what's called a high strain rate here, and the flame is actually being stretched because of the flow wanting to actually go this way on either side. As a matter of fact, you could also have a premix flame configuration here in the opposed jet burner. How would you do that? You could now have a fuel and oxidizer coming from the same nozzle, let's say from the bottom, and then you now send a opposed jet of inert gas, let's say nitrogen, right? And what would this do? It would now create like a stagnation point flow. So this is essentially what's called as a stagnation point flow, because by symmetry this would be as if like you had one jet that is impinging on a wall. So if you now have a jet that is impinging on a wall, it just spreads out and you have a stagnation point right at the middle, right? So this creates like a stagnation point flow in the middle, and essentially both the flows together now are like mirror images of each other if the velocities are the same, and so you have a stagnation point flow, and you could have a premix flame which is flat, which is subjected to a strain, right? That's an experiment to actually investigate the effect of the strain rate on the premix flame. But in the case of diffusion flame, you can actually hope to get a flat diffusion flame, as opposed to in this case what's going to happen is the flame could actually be curved depending upon whether you have we will talk about this in greater detail pretty soon, depending upon the stoichiometry of the mixture, right? So you could actually have a dilute mixture for the fuel or dilute mixture for the oxidizer. For example, if you use air, then it's already diluted with a lot of nitrogen for the oxygen, and then it depends on the stoichiometric coefficients in the reaction. Like the stoichiometric coefficients means if we need more oxidizer for a given amount of fuel for stoichiometric reaction and so on. So these things will actually dictate what the shape of the flame is, but you can't really expect to have a flat flame. Okay, so if you want to have, and the reason why we would like to have a flat flame, for example, is if you want to treat it in a one-dimensional manner, right? But there are ways of one-dimensionalizing these flames and so on. We'll discuss those things in greater detail. But effectively, you could think about two configurations like a Coflow and a Counterflow geometry, which makes more sense in the context of diffusion flames now. What we will do now is actually pick the Coflow geometry and then look at what's called as the Burke-Schumann problem. Now the Burke-Schumann problem is a very fundamental problem. In fact, it was presented in the first symposium on combustion in 1928 by Burke-Schumann, and it was subsequently published in the Journal of Industrial Chemistry. So it's a very celebrated piece of work, and it's had numerous citations subsequently and lots of different extensions to this problem. And the name, the phrase Burke-Schumann flame connotes a certain set of assumptions that it embodies, and it refers to certain limits of like very high activation energy, infinite rate chemistry, and so on. So the Burke-Schumann problem is as follows. I'll describe the problem first and then list out the assumptions that are involved in this. The Burke-Schumann problem is essentially that of two concentric ducts. You could do this problem in a Cartesian coordinate system where you have like two channels, right? So this is like infinite plates, and this is also infinite plates. So these are essentially two coaxial channels. Or you can also do this in an axisymmetric manner. That means you're actually having two circular pipes that are concentric to each other. And the original Burke-Schumann problem was done as a pipe problem. So it is an axisymmetric problem. And the inner pipe terminates at a particular point. The outer pipe extends to infinity. So the inner pipe is a semi-infinite pipe. It's coming from infinity below and up to this point. The outer pipe is infinite all the way, right, on either side. And you have a fuel coming in at a certain mass fraction YF naught inside on the inner duct, and you have oxidizer coming in the outer duct at a oxidizer mass fraction of YO naught. So these are the inlet mass fractions. All right, and they are also coming in at all the flow, both the flows are actually at the same velocity u. So it is actually uniform velocity, and we are basically supposing that you have a uniform flow everywhere at this velocity. Alright. We are going to adopt the Schwab-Zeldovich formulation, where we are going to solve only the species equation and the energy equation. Perhaps we will actually find that we will also make other assumptions that requires us to solve only the species equation and not the energy equation, and we can decouple them. Therefore we are not going to solve the momentum equation, we are going to prescribe the velocity field, and the velocity field that we will prescribe here is just uniform velocity everywhere for any point in the flow, for any mixture, whether you have only reactant, only product, a mixture of reactant and product, only product, or only fuel, only oxidizer among the reactants, whichever way, right. So everywhere you are basically going to say the same velocity exists. Now of course this is not a good assumption, okay. For several reasons. You could first of all think, wait a minute, I am looking at pipe flow, shouldn't I actually have something like a parabolic velocity profile if it is laminar, right, and then parabolic velocity profiles for the outer flow and so on. Then what about the no slip boundary condition of these walls for this velocity profile? Let us not worry about all those things. That is all a fluid mechanics person's problem, okay. I am not going to worry about all these things, I am going to worry only about the combustion problem. The second thing is we are not going to bother about the density variation with temperature. So if the density varies with temperature, then as there is a flame and the flow goes through the flame, it expands because of thermal expansion, and therefore when the density changes, the velocity will change as well, right, and then the velocity field will now depend on the flame. But that is now like a convoluted problem. I need to prescribe a flow field in order to actually work out the flame, and the flame is now going to change the flow field. So what do I prescribe? So that's a problem that I will have to reckon with if I have to couple the flow and the combustion problems together, right. If I want to keep them separate, I will simply have to prescribe a velocity field in spite of the flame. That means I shouldn't worry about the effect of the flame on the flow field. This is reasonable because pretty much up to the point where the flow is heating the flame, it is not expanding. So, and it is a convective situation of all the flow that is going out. So all the expansion is happening downstream of the flame. So it's an approximation, all right, but still it's a reasonable one, okay. So this is typically the problem. The question that we are asking in this problem is, what is the flame shape, and this is very, very important when compared to what is the flame structure, okay. In the context of premixed flames, I have clarified the distinction between a flame shape and a flame structure. So when we are looking at one dimensional premixed flames, right, we were saying let's look at the preheat zone, let's look at the reaction zone, let's look at how the temperature increases and then tapers off, and how does the reactant concentration falls in the preheat zone and then tapers off at a low value, all these things, and how does the reaction rate grow and all those things, right. Now that is looking at the structure. When you now look at the structure of the flame, that means you are looking at the spatial variation in temperature profiles, concentration profiles, and reaction rate profiles, and so on, right. Shape of the flame in the context of premixed flames was something to do with like a conical flame above a Bunsen burner, or a wedge flame in the case of a ramjet, and so on. So that is like a gross thing, and it's almost like we are looking at a sheet of a flame wherein the structure really happens, right. And then the way we were actually handling it is by looking at the G equation and how the flame propagates with a certain flow speed and balances the normal component of the flow. Those things that is what we were doing. Here again it is sufficient for us, the way Burke and Schumann posed this problem, to work out the shape of the flame, okay. And so what we are expecting is the shape of the flame to look somewhat like this, or somewhat like that, right, or somewhat like this. I don't know, that's something that I'm going to work out. So if you can imagine like a candle flame is something that's like a teardrop kind of shape, right. You could also have like a tent shaped flame, or if you had a fuel if you had a lot of fuel that is trying to actually mix with the oxidizer, the flame could open up, right. Many times when you keep in mind when you're looking at flames that are opening up, it could be like a jet flame. So a jet flame is where you could have like a very high velocity fuel and very low velocity oxidizer, then you are mixing up in your mind the shear layer effects like momentum transport because of velocity gradients, and you have a jet that is coming up, entrainment and all those things, okay. It's possible to think about all these things that we are talking about in that context also, but the fact that you are having a uniform velocity is to remove any effects of shear layers from this, and we are looking at only species mixing and no momentum mixing effects, no thermal mixing effects, none of these things is brought into picture, right. So it's a very nicely posed problem in the sense it clearly focuses on primarily two things. One is that there are only two things that are happening here primarily. One, you have a axial convection of species, and when I say species, we are talking about reactants that are separate to begin with, and then mixture of reactants somewhere in the middle, and products also coming up as we go, and then fully products later on. So you see it's not as nicely done as a one-dimensional premix flame previously. So we had reactants here, you had a flame, you had products there, right. That was more of a black and white thing, okay, and with very little fuzziness. If you now go from here to there, and then keep scanning across, you will find all kinds of things that are happening up from the point where you had separate reactants and complete mixed up products at the top, right. So we have to now evolve how this flame shape is happening. So one of the things that's happening, regardless of whether it is reactants that are separate or products that are combined, is axial convection of species, and it is balanced by radial diffusion of species, okay. You also have some axial diffusion, all right. I'll explain this a lot more carefully little later, but the two primary things that are of most importance in a Burke-Schumann diffusion flame are axial convection and radial diffusion. So this is the balance that we are basically talking about, which is how well do the species diffuse while they are busy convecting, right. This is what is going to dictate how the flame shapes up, right. So the flame shape is essentially dictated by the balance of axial convection and radial diffusion. So once you get the flame shape, the question of industrial interest for you is what is the flame height, right. So for example, if you now want to design a furnace or a burner or a combustor and so on, and you want to light up a flame at the burner, you want to know how long you want to have the combustor walls, right. So you want to be able to cover up until the tip of the flame at least, so that you can ensure complete combustion within the combustor. So the height of the flame is of practical interest, right. So the way Burke and Schumann actually tried to get the flame height was to actually solve for the flame shape, and once you get the flame shape, you now find out where it actually stops, at the center line or at the walls, what is the vertical distance over which it spans, and that's the height of the flame, right. So you can obtain this. So this is basically the way the problem is posed, and the solution procedure is to go through the shape of the flame. So they adopt the Schwab-Zeldovich formulation. So right, and the Schwab-Zeldovich formulation, recall, comes with about 11 assumptions, right. And we did this adoption even when we started analyzing the premix flame structure, and we went through some additional assumptions, maybe about 2 or 3, right. So here again we will have to go through additional assumptions, some of which I have already stated. So the first assumption, so further assumptions, Number one, if you now set up a coordinate system that is centered at the mouth of the fuel duct in the middle, and then say call this R and call this Z, then let us say the Vz component of velocity is u, which is a constant, right, given. Unlike in the case of premixed flames where this is not given, this is actually an eigenvalue, you need to find out what is the flow velocity at which you have a flame that is stabilized. We do not have to worry about the flame stabilization problem in the case of in the case of the diffusion flame as it is posed by Burke-Schumann, and that is very important for you to think about. We will have to see later on what the stabilization mechanism is, and we will bring in some elements of premixedness that is coming up. That is the reason why we call it, it is not exactly entirely a diffusion flame, we would simply call it a non-premixed flame. But so we will not worry about stabilization issues, this is given. And correspondingly we say Vr is equal to 0, that means you do not have any radial velocities. Strictly speaking this is not true. If you were to allow for the density to vary with temperature, you will now have the flow diverge, similar to the way we saw in the conical premixed flame, and that will acquire a radial velocity component, but we are disregarding this, right. The second assumption is the mass fluxes are equal. That is rho v fuel equals rho v oxidizer, right. Now putting things together, what this basically means is that if the velocities of the two fluids are the same, right, and this is the velocity field that is given there, that means the fuel and oxidizer, all of them have, both of them have the same velocity. If the velocities are the same and the mass fluxes are the same, that is simply means that the densities are the same, and densities being the same is essentially what it amounts to saying the density does not vary, right. So the density does not vary not only because of temperature but also because originally the densities were the same, so you do not really have to worry about any change in density in the first place. And how does that, is it possible? Is it possible to have a fuel and oxidizer of the same density, right? The answer is in the laboratory it is possible to mix the fuel and oxidizer with different diluents in such a way that you achieve the same density for these diluted mixtures of fuel and oxidizer, right. So we say YF0 and YO0. So in this you have basically fuel with a diluent, because 1 minus YF0 should be the diluent. In the outer annular duct you are having 1 minus YO0 is a diluent. You could choose these diluents in such a way that the densities are the same, right. The next assumption is certainly a simplifying assumption, which is rho d is a constant, and this simplification is required from a mathematical standpoint, right. And of course what this means is that if the density is constant, d must be the same everywhere, okay. That is part of the Schwab-Zeldovich formulation anyway, right. So we are not looking at variation in d across. The fourth assumption is diffusion in the axial direction is negligible. Diffusion in the axial direction is negligible, that means we are saying it is negligible relative to the radial diffusion, okay. So that means we are saying wherever we have a dou z squared is much less when compared to partial squared yi over partial r squared, right. Now this is to basically say that we are interested only in retaining the radial diffusion. The convection is axial because we have disregarded any radial convection by this assumption, right. So we are prescribing a velocity field that is only axially convective, and we now permit only radial diffusion so that we can clearly see the balance between axial convection and radial diffusion. I want to point out that this assumption is not necessary. You could keep the radial diffusion and sorry, we could keep the axial diffusion and show that the axial diffusion is important when you have a small Peclet number, or it is negligible truly when compared to the radial diffusion for large Peclet numbers, and large could be for laminar flows greater than 10 is large enough, 10, 20 or 50 maybe is large enough, right, but less than 5 is something that you have to keep. And what I will do is I will keep talking about the consequences of retaining the axial diffusion, but I won't solve that problem, alright. And it's interestingly, I think in this was actually published in 1928, as I said. I think it's 1982 or 84, there was a combustion science and technology paper by Chung and Law that actually publishes the solution with axial diffusion retained, okay. So the interesting thing about these things is, as and when people make more and more assumptions, long later there could be somebody who relaxes an assumption, and then you now have a expanded version of this, or a more general version of this solution that's possible. As a matter of fact, we're talking about a Burke-Schumann problem adopting the Schwab-Zeldovich formulation, which essentially is a steady state problem, right. So we're looking at a steady state situation. That means this flame is not going to change shape with time. And very recently, in about 3-4 years ago, we relaxed the steady state assumption and actually did an oscillatory diffusion Burke-Schumann flame, alright. So what I mean to say is, you could relax many of these assumptions and solve the Burke-Schumann problem, and these things over a period of time begin to come into your exams and homework problems and assignments and all those things, right. The fifth assumption is perhaps the most important and insightful assumption that needs to be considered. What we are thinking here is, we say, what are the right words? Yes, it's called the flame sheet assumption, right. Flame sheet assumption means similar to how we adopted the G equation, where we said the flame is essentially going to be a sheet. It's a surface of discontinuity between reactants and products. In the case of the premixed flame, as I said, in this problem we are interested only in the shape, we are not interested in the structure, so it's sufficient for us to think about like a sheet, right. Therefore we want to actually make the assumption that the flame is going to be a sheet. The question is, what is it that we are going to do in the equations that implements this assumption, right. What is the consequence of this assumption in terms of our analysis? What does it really mean, okay, physically? What this really means is, this directly corresponds to what is called as infinite rate chemistry. Infinite rate chemistry or infinite kinetics, infinite kinetics. The other name for this is what is called as the mixed is burnt, approach. So this requires some explanation. What we are basically saying is, and this is very, very important, this assumption means that the reactants react instantaneously when they mix in stoichiometric proportions. Okay, and again that needs to be further explained. What we mean by stoichiometric proportions is you now have the fuel and oxidizer that are mixing, right? So if you now think about even like a splitter plate problem, let's suppose you didn't even have these walls, right? You simply had only a splitter plate, and this is a semi-infinite domain, that's a semi-infinite domain, and you had a plate that just stopped here, and you had all fuel coming in this side, all oxidizer coming in that side. This is to say we are focusing on one lip here, right? Let's not worry about what's on the other side. Then slowly what's happening is as the fuel and oxidizer are actually flowing out, they are beginning to mix, right? So as they begin to mix, if you are somewhere very far away, you're not going to know that they are mixing. That means it's all fuel. If you're on this side very far away, you're not going to know that they're mixing, it's all oxidizer. But as you keep going from here to there, all oxidizer becomes all fuel through a state where you have a mixture, right? That means there is going to be some particular contour where the fuel and oxidizer are actually finding themselves mixed in stoichiometric proportions, right? And what we are saying in this assumption is the flame is going to be a sheet that is coincident with the stoichiometric contour in the mixing field, right? So let's just write that. The flame is a sheet coinciding with the stoichiometric contour in the mixing field. We will elaborate this a lot more after we go through the Burke-Schumann solution, but at this stage I think I'll just give you a peek of what is going to happen. Let us suppose that we do not have this assumption and we have what's called as a finite rate chemistry or finite kinetics, okay, and that is what is reality. In reality, if you now work out the Arrhenius law or the law of mass action for the reaction rates, you're going to get some number, right? Then that number is going to be large, all right, for most combustion things, but it's still finite. Let's say it's finite. As the fuel and oxidizer are getting together, right, you're going to have more and more reactions happening if you find sufficient amount of fuel and oxidizer at a place, because the law of mass action requires for the reaction rates to have concentrations of both fuel and oxidizer. If you went a little bit farther away and you found that you had only fuel and not much oxidizer that is mixed in, you're going to have the reaction rates drop substantially. If you go on this side and you find that you have more of oxidizer and you didn't have hardly any fuel mixed to all the side, you're not going to have concentration of fuel, the reaction rates are going to drop substantially. As a matter of fact, if you think about the premix flame, you had a certain reaction zone thickness which was restricted because you were running out of the diffusion fuel. That means the reactant concentration comes almost to zero, right? Here the reactant concentration comes to zero from opposite sides for the two reactants. There both the reactants were actually coming from the same side of the flame. Here the two reactants are coming or diffusing from opposite sides of the flame, so both reactants will have to actually go to zero concentration on either side, and then that is going to restrict the region of your reaction zone, right? Where is it going to be like highly reactive? So if you now think about the reaction rates, they are kind of hitting zero at these ends where you're running out of fuel on one side and running out of oxidizer on the other side, and you now have a peak in the reaction rate along the stoichiometric surface, right? That's where they are available in equal abundance, so to speak, right? Then we now say well, let's want to have a flame sheet. I don't want to have thick flame, right? So if you want to have a flame sheet, I now have to collapse this to a particular to a sheet, right? Where would I collapse it? Obviously at the stoichiometric surface. Therefore, we can imagine that this is a remarkable insight that Burke-Schumann had back in 1928, when there wasn't too much combustion theory that was going on at the time, right? So the flame sheet obviously now can be convincingly thought of as coinciding with the stoichiometric surface in the mixing field. If you now assume this, we have a extremely simplified situation, which is we don't have to solve the combustion problem at all. It is sufficient for us to solve the mixing problem. It could be as if we are doing a cold flow mixing without igniting. So you just have to send the fuel in, you just don't send the oxidizer there, they mix, and then they will mix at a stoichiometric proportion. Wherever they are mixing in stoichiometric proportion is where the flame is supposed to be, right? Whether you ignite it or not. Okay, I just want to find that. Therefore, I don't have to actually worry about the energy equation along with the species equation. In fact, it is sufficient for me to actually worry only about the species equation of the fuel and oxidizer. I don't even have to worry about other species, right? And see how the species dynamics is going to work out for fuel and oxidizer alone. I don't worry about energy. So in the Schwab-Zeldovich equation set of n+1 equations, I will just focus only on two equations which correspond to the species conservation of fuel and oxidizer alone, and then work out the mixing problem, right? So this is how this is going to happen. So the Schwab-Zeldovich set, we just consider the species conservation equations of fuel and oxidizer species only. And first of all, for any species, your Schwab-Zeldovich formulation is divergence of rho v yi minus rho d grad yi equals omega I, or I think we had the symbol wi, that's wi, right? And what you're going to consider here is I equals O and F. This is a step before we form the alphas and the betas. If you go back to the Schwab-Zeldovich formulation, right? So it's for the sake of refreshing your minds, this is the species equation, the Schwab-Zeldovich species equation, okay? And then we formed an alpha such that you will now divide these by something and get only a omega here, and that is common for all the right hand sides. And we would also do a particular alpha t for the energy equation, which you're not going to consider here, so that you'll still get an omega there. And then you can start subtracting one from the other two, and by forming betas, which are like alpha minus alpha 1 or something of that sort. We will try to do something like that here right now, but at the moment we are going to consider only I equals O and F. We don't worry about anything else at the moment. So we now form the alphas. So let's say we have an alpha I, which is yi divided by wi nu I single prime. Now of course the Schwab-Zeldovich formulation is for a single step reaction. So single step reaction we are looking at is nu F plus nu OO gives products, we are interested only along this only in the stoichiometric surface, and the stoichiometric surface, this is the stoichiometric reaction, right. So nu f and nu o are stoichiometric coefficients of f and o, okay, such that you get only products, you don't get anything more, right. And therefore in this case, if we now compare this with the template reaction reaction that we have, which is like nu I single prime sigma I equals 1 to capital N, nu I single prime script mi gives sigma I equals 1 to capital N nu I double prime script mi, and that is where you will get your nu I double prime minus nu I single prime for the alpha definition. Here nu I equal to nu I double primes are equal to 0, and nu I single prime are essentially nu f and nu o, okay, which means alpha f equals minus yf divided by wf nu f, and alpha o equals minus yo divided by wo nu o, all right. And wi divided by capital Wi nu I double prime minus nu I single prime is equal to omega, right. Therefore we get divergence of rho v yf, sorry, you can directly write alpha f minus rho d gradient alpha f equals omega, and divergence of rho v vector alpha o minus rho d gradient alpha o equals omega. So now form beta. This is the last step in the Schwab-Zeldovich formulation. In this case we now say let beta equals alpha f minus alpha o. If you do this, then we get divergence of rho v beta minus rho d gradient beta equal to 0. This is amazing because this is a combustion problem where we don't have to solve, we don't have to consider chemical reactions, okay. And look at what we have been doing so far. The last time we solved the Schwab-Zeldovich formulation for a premixed flame, we looked at the preheat zone separately from the reaction zone, and in the preheat zone we had a convective diffusive balance, which means we had to consider convection and diffusion only, and in the reaction zone we had a reactive diffusive balance, which means we had to consider only the diffusion and reaction only. The full combustion problem in general always has a minimum of convection, diffusion and reaction. These are the three elements that constitute combustion primarily, right. We escaped trying to solve all three of them together at that time by dividing it into two parts where we consider two of them to get at a time, and here on the whole we are evading the consideration of reaction rates completely, and we are looking at it as only a convective diffusive balance, except here we are going to specifically say it's a axial convection versus a radial diffusion, right. So it's a two-dimensional problem, and therefore that allows us to actually make these distinctions between axial convection and radial diffusion, but there it was a one-dimensional problem, so we didn't have that liberty, okay. So this is a hallmark of classical combustion solutions. We try to avoid situations where we have to deal with all three of them together. That is what is called as a mixed problem, okay. So we try to avoid these mixed problems. We always consider two processes at a time balancing each other wherever that is possible, and you now get in this context a homogeneous linear equation, right. And we now adopt cylindrical polar coordinates. So far we have not done that in the governing equations. Adopt cylindrical polar coordinates, use v vector is equal to u e z cap, and dou squared beta over dou z squared much less when compared to dou squared beta dou r squared. That is going to happen here in the second term, right. So with all these assumptions we are simply going to have u divided by d partial beta over partial z equal to 1 over r partial derivative with respect to r of r partial beta over partial r. This is the r component of the Laplacian in cylindrical polar coordinates, and so it is a bit complicated there because of the cylindrical polar coordinate. Now for the first time we need to worry about boundary conditions. We got the simplified governing equation which is this, and let us now look at the boundary conditions. Okay, the boundary condition that we require is in beta. Okay, so we need boundary condition for beta. Beta is now our single variable and it is a single equation that's governing it, and we need boundary condition for beta in r and z. Okay, and since it's governed to second order in r, you need two boundary conditions, and since it's governed to first order in z, you need only one boundary condition in z, right. So if you now look at the boundary conditions that are supposed to be in r, for the two boundary conditions in r we have to look at what is the domain. The domain for us is going from r equal to 0 to r equals, let us say we want to now distinguish between the inner duct radius, so let us call this A, and the outer duct radius which is B. So our domain is going from r equals 0 to r equals B, so we have to supply a boundary condition at r equal to 0, right, and that is a symmetry boundary condition. So BC at for all z, right, at r equal to 0 partial beta over partial r is equal to 0, this is the symmetry boundary condition. Alright. Now what is the first derivative of beta actually imply physically? If you now go back, beta is nothing but alpha f minus alpha o, and what is alpha? Alpha is yf divided by wf nu f, and similarly alpha o. So this ultimately goes back to taking partial derivative of r of yf and yo with respect to r, right. So partial derivatives of mass fractions amount to diffusion fluxes, right. So what we are saying by symmetry, that partial beta over partial r should be equal to 0, means that you don't have diffusion across the center line because of symmetry, right. So whatever is happening here should actually be the same thing that happens there, and if you now have a diffusion over here, that means that also means that you have to allow for diffusion from that side to this side, that indicates accumulation, which is not possible, right. So you need to have, that's what symmetry boundary condition is all about, it is physical, okay. And at r equals B you have a wall, and when you have a wall you can't have species diffuse. Species is not going to convect to the across because you have only u, that's like kind of like the no slip of, I shouldn't say no slip, this is like a inviscid flow that is slipping past the wall, but it doesn't penetrate the wall by convection, but it can't diffuse. This is a diffusion problem. Therefore we still have to say that partial beta over partial r is equal to 0, this is wall BC. okay, no diffusion across the wall. Now what we have seen here is we have two Neumann boundary conditions, right. We have to count on the third boundary where we need to have a boundary condition which is z equal to 0 to provide something Dirichlet so that we will be able to peg the value of the problem. If you had Neumann BC here as well, then your solution will not be unique, right. In order to get a unique solution we should look for some Dirichlet boundary condition on at the Berner lip right here at z equal to 0, which we will consider tomorrow.